Hi. Throughout our everyday lives, we seek things to be balanced, whether it be our diets, the scales in our kitchen, or the seesaw your kids play on. In chemistry, however, balance comes in the form of equilibrium, and any chemical reaction seen with this symbol indicates an equilibrium reaction. But what affects the system at equilibrium, and how does the system react? Let's start with some basics. All chemical reactions have a specific amount of energy required to break and form bonds, and this is known as the activation energy. An energy profile diagram highlights not only the activation energy, but also shows whether a reaction is endothermic or exothermic. Reactions are mostly one way because of the largely different activation energies different reactions have, meaning the direction with the lowest activation energy is favoured. But what happens if both activation energies are low? This is what is needed for an equilibrium reaction to occur. Chemical equilibrium occurs when the forward and reverse reactions are occurring at the same rate. Chemical equilibrium has no macroscopic changes as the reactions are occurring so quickly that there is no change in concentrations and no net chemical change. So although there is a whole magnitude of reactions occurring at the same time, an observer would have no indication the system is in chemical equilibrium and it would appear no reaction is taking place at all. So what happens when you disturb a system at chemical equilibrium? Well, let's have a brief overview of the changes that we can impose on such a system. We could add a catalyst, add or remove heat energy, increase or decrease the pressure, or increase or decrease the concentration of a species. First, let's look at what happens when you add a catalyst to a chemical system. A catalyst is an agent added to a chemical system to lower the activation energy and hence speed up a reaction. When a catalyst is added to an equilibrium system, no change in equilibrium occurs, but the time needed to reach equilibrium decreases. Let's investigate the molecular level of a chemical reaction. Here we have a chemical reaction where the species red and blue form to create a red and blue molecule. When the red and blue molecules collide at an appropriate angle with sufficient energy, they will come together to create a new bond. According to the kinetic theory of heat, molecules with higher heat energy have higher kinetic energy, and as such have higher chance of colliding, and hence a higher chance of reacting. This can be seen in the Maxwell-Boltzmann distribution curve. The Maxwell-Boltzmann distribution curve shows the distribution of kinetic energy for a gas at a specific temperature. It shows that at a higher temperature, more particles have a higher energy, and therefore more particles are likely to react. To understand further, we must understand what Le Chatelier's principle is. Le Chatelier's principle states that the system at equilibrium undergoing disturbance will react accordingly to minimize and counteract the disturbance. Although it may not be clear at first what this means, it will become very clear once we go through temperature, which is the next step. When heat energy is added into a system at equilibrium, the molecules within that system will have a higher kinetic energy. According to Le Chatelier's principle, the system will want to minimize and counteract the disturbance. The best way to counteract heat is to remove it, and to do that the equilibrium reaction must run endothermic. Since an endothermic reaction absorbs heat, the reaction must run endothermic to absorb the excess heat energy. Similarly, when heat is removed from a system at chemical equilibrium, the system seeks to counteract it by replacing that heat energy, and hence runs exothermic. In a closed system, if heat energy is added, it will slowly radiate that heat and hence slowly shift equilibrium in the other direction. What occurs when the concentration changes? When the concentration is increased, at the molecular level there are more particles to collide together, meaning it's more likely for a reaction to occur. So therefore, if the concentration of reactants is increased, the forward reaction will be favoured, and the concentration of reactants will slowly lower as the reaction approaches dynamic equilibrium. If, however, the concentration of reactants is decreased, there will be less particles for the system to react with, meaning the forward reaction is less likely to occur. Therefore, the reverse reaction will be favoured, and the concentration of reactants will slowly increase. In terms of Le Chatelier's principle, if the concentration is increased, the system will seek to counteract this change by slowly lowering the concentration again until the system is in chemical equilibrium. The only way the system can lower the concentration is by using the species in a reaction. Finally, let's look at pressure and volume. To make things easier, it is important to note that a decrease in volume is the same as an increase in pressure, which is the same as an increase in concentration. This is because pressure is caused by the collisions of gas molecules within their container, so if there is less room to move around in, the particles collide with the container more often. It is also important to note that the concentration is the measure of moles of a substance in a specific volume. So if the volume decreases, the substance is more concentrated. So it could be said that a decrease in volume or an increase in pressure results in the same shift as an increase of concentration, right? Well, not exactly. When we are talking about gases, when the pressure is increased, the system will seek to counteract the increase by decreasing the pressure. The system can do this by reducing the number of moles in the system, and it can only do this by pushing the reaction in the direction of the least amount of moles. At the molecular level, when the volume is decreased, the particles that take up the most moles are the most likely to react, and as such will cause a reaction leading to less moles. But what happens if the number of moles are equal on both sides? Well, it means no change in equilibrium will occur. Let's do an example. Here we have the equilibrium reaction of clear dinitrogen tetroxide and reddish-brown nitrogen dioxide. We will be investigating what occurs when we impose change onto the equilibrium system. Firstly, when we decrease the volume and inherently increase the pressure, the reaction favours the reverse reaction because it has the least number of moles, and as such the reddish-brown colour disappears. Let's look at heat energy now. When we turn on our blowtorch, the forward reaction is favoured. The excess heat energy must be removed, and since the forward reaction is endothermic, it's the way to go. Since more nitrogen dioxide is being produced, the red intensity increases. Once we turn off our blowtorch, the system is allowed to cool. As it cools, the nitrogen dioxide turns into dinitrogen tetroxide, and the red hue disappears. Finally, we have our increase in concentrations. We have a gas cylinder of nitrogen dioxide, and as we add more gas into our system, the nitrogen dioxide is converted into dinitrogen tetroxide, removing the red hue. This is because Le Chatelier's principle dictates that to minimize the disturbance of adding concentration, the system must reduce the concentration by running in the other direction. So let's do a recap of everything we've learned. For an equilibrium reaction to occur, the activation energies of both directions of a reaction must be low. Equilibrium occurs when the forward and reverse reaction rates are equal. A system of dynamic equilibrium will have no macroscopic changes and cannot be observed directly. If a catalyst is added to an equilibrium system, there will be no shift in equilibrium, but the time required to reach equilibrium will decrease. Heat energy shifts equilibrium in the direction required to remove excess heat energy or restore removed heat energy. Similarly, a concentration change will shift equilibrium in the direction required to remove excess concentrations or restore removed concentrations. Although a decrease in volume is the same as an increase in pressure, which is also the same as an increase in concentration, they do not shift equilibrium similarly. If the pressure is increased or the volume is decreased of a gas in equilibrium, it will shift in a direction with the least amount of moles. If the number of moles on both sides of the reaction are equal, no shift in equilibrium will occur. I hope you learned something today. Bye!